Thanks. Heavenly Father, we thank you for this day. I thank you for the break. I thank you, Lord, that you love us independent of what we do. That you're a good God and a righteous God, Lord. And we just thank you for this day as you again would glorify. You be glorified in what we do this day, Lord. In your name I pray. Amen. Okay, so you should turn in your take-home quiz. Shinku, shinku. I am, I had to grade the quiz myself, so the grading is generous. So if you look at quiz 6 here, Mr. Cho all the way in the back, behind you, and behind you, and in the blue. I think, I'm not sure where he's sitting. Joey. Try not to say names at the moment. Let's see here. No. All the way in the back. All the way in the back. Actually, also all the way in the back. Again, turn your quiz 7 in. Hand it over. I'll pick them up here in a second. Where's Paul? Here. You can just set it there, it's fine. We only take off half the points for no staples. Grant? Sorry. Matthew. Nathaniel. Oh, right. Is there a Mark? Anthony? Mark Anthony. Sorry. Becky? I had to do some detective work on that one. Let's see here. Joey? Travis? Andrew? Anybody here who did not get their quiz 6? Oh, there you are. You're on the next list. Anybody else? All right. Oh, I'm sorry. Here, I'll give you the stack. All right. Oh, thanks. So I should have a solution to quiz 6. So quiz 6 here. So I got all the quiz 7s now? Thanks. So let's just talk about quiz 6 real briefly. Find the greatest lower bound and least upper bound if they exist of this set. So basically to find the greatest lower bound and least upper bound of a set, you have to kind of get your hands dirty and like somehow understand what the set is, right? And so for this personally, I just plugged in a couple numbers, got a sense of what it was doing. Decreasing. What? That's not decreasing. Idiot. Increasing, obviously, right? I mean, the 1/4, 1/9 thing is decreasing, which is what I was thinking about. This does not bode well for today.
Oh, good. Yeah, it goes 2 to
Oh. Oh no.
You're good.
Oh. I need to drink more of this. All right, well, now that we got that out of our system, it's decreasing, which means that its first element is its largest element, right? So the 2 serves not only as the first thing, but also as a maximum for the sequence. So, of course, that will serve as the least upper bound. In fact, it's the maximum of the range of the sequence, of the set, the max of the sets. And the greatest lower bound is pretty clearly 1, right? So it never gets to 1, it's always above 1, so 1 is the greatest lower bound. I think a fair number of you got that. If you didn't get it right, I probably didn't take off points if it looked like you tried something there. I wasn't super critical in my grading of this one. Almost everybody here didn't show proper work for this. All right, with about maybe 3 exceptions. And some of you I didn't give any points because what you wrote was just stone cold crazy. But some of you wrote something that was kind of like, I don't know, there's a lot of wrongness I saw here. But basically the point is, this is like that 2 to the n over n factorial homework problem, right? Remember the one we looked at? And so it's the same kind of thing, just write out 3 to the n, write out n factorial, and pick some starting point which serves their purposes. N greater than or equal to 4 will do nicely, because then that means that this is either, if n is greater than or equal to 4, this is greater than or equal to 3, right? And this is greater than or equal to what? 2. And the point is that this largest thing here is 3, right? So these are all at most 1, and they're usually less than 1, right? Until you get to this right here, right? Okay, be careful not to go past that. So these are definitely less than, if I replace this with 1 times 1 times 1 times 1 times 1, that's larger than this product. So I can replace this whole mess with just the 3 over n and the 3 times 3 over 2 times 1, which is 9/2. So I get 27 over 2n is above 3 to the n over n factorial, and 0 is below. Some of you had something other than this, and I think if you look at it, you'll find you're wrong. I'm not 100% sure you're wrong. I haven't graded the quiz that carefully, so I'm not absolutely sure you're wrong, but I know this is right. So, comments, Mr. Kang? No? No comment? Okay. Anyway, the basic idea here is that we can put 0 below this, and we can put something over n above it, and then the squeeze theorem finishes the job, right? This goes to 0, that goes to 0, of course, then this has to also go to 0 by the squeeze theorem. So, I was, relatively happy if I saw you say the word squeeze theorem and wrote down some inequality, which was well-intentioned, but slightly wrong. Like, it's okay. I wasn't too picky. I didn't take off points here if you didn't say extending n to be continuous, but I might on the test, all right? So, basically here it is. This is n e to the minus n. So that's n over e to the n by, algebra. The definition of e to the minus n, if you like. Whatever floats your boat. Then I apply L'Hopital's rule, infinity over infinity, which gives me derivative of n, which is 1. Derivative of e to the n with respect to n is e to the n. So then this goes to 0. So the answer is 0 here. This one, I saw you guys, a lot of you, maybe half of you, were just kind of like trying to guess something here and just try to like hobble something together from what we've done before. Which I know if you're operating from a state of partial understanding is all you can do, right? But you need to replace that partial understanding with much better understanding tomorrow. Otherwise, it's going to hurt you. I don't want it to hurt you, but it will. Like, you need to understand what we're doing here carefully and and be able to reproduce this in its entirety, all right? Not necessarily this problem precisely, but problems like this you ought to be able to do. These are not like esoteric, weird, off-the-wall, optional problems. These are like straight down the center of Main Street, like this is what the course is about kind of problem. I mean, it's there. Whatever. So the point is, this is an indeterminate power. It's 1 to the infinity. So I do the exponential log trick, pull out the limit using the continuity of the log, pull the x down by properties of the log, and then I've got this star limit to work with. I rewrite the x as 1 over x because it serves our purposes. That gives us log of 1 as x goes to infinity, which is 0, and 1 over x as x goes to infinity is 0, so it's this type 0 over 0 up here. And then L'Hopital's rule, differentiate the top, differentiate the bottom. Derivative of the top is 1 over the argument of the log times chain rule. Derivative of this gives me minus 2 over x squared. Derivative of that gives me minus 1 over x squared. There's a residual 2 which survives. I get 2 over 1 plus 2 over x. I think some of you had this and then said this is equal to 1, which is like snatching victory from defeat from the jaws of victory. That's what I wanted. Let's see here. Anyway, so this of course is equal to 2 because as x goes to infinity, this goes to 0, right? And it leaves us 2 over 1 plus 0, which is 2. And then you put that back up in here and we get e squared, right? So the answer here was e squared. Any questions about these? I don't think this was a particularly difficult quiz. I mean, the time was a little bit oppressive, right? But I would hope you could do these problems if you had more time, right? Or problems like them, yep.
I still don't understand how, when you're doing the L'Hopital's rule, how, like, 0 over 0 is equal to infinity. Can you just explain how you know that?
How I know that?
Like, just,
I mean, how I know that it is the right kind of thing, or... So the reason that we get, someday I'm going to get the guy in here before me to erase the board, but let's see here. Jerk. Let's see here. Basically, if you have 0 times infinity, right, you got 2 choices. So this is like, say, f times g. So in other words, the limit of f is 0, the limit of g is infinity. You got 2 options when you have this pattern. You can either go to something like f over 1 over g, right? And if g goes to infinity, 1 over g is going to go to 0. So this will change it into a type 0 over 0 problem. Or if you've got 0 times infinity, you can keep the g put, and you can move the f downstairs like this. Right? So when I'm faced with something like x, e to the minus x, for example, just to change the letter for a second here, and x, it's all the same, right? So this is my, I guess I turned the tables here, right? This one's going to infinity, right? And this one's going to 0, type infinity, type 0. So I can either say, I got 2 choices, right? I can either go limit x goes to infinity, I can leave the x stay put, and I can move the e to the x downstairs, like so. Or that's also equal to, e to the minus x over 1 over x, right? So this is type what? This is type infinity over infinity, whereas this one is type 0 over 0. The original one was type infinity times 0. All of these are indeterminate. In other words, you can't just read the limit off them just from what's already there. You have to do something else, algebra or L'Hopital's rule or something to resolve the indeterminacy to be able to figure out what the limit's actually equal to. And the point of my example here is you definitely don't want to do this here, right? Like this. No. This is not helpful, right? Because when you do L'Hopital's rule on this, it gives you minus e to the minus x over minus 1 over x squared, which is still 0 over 0 and more so. It's kind of like a worse indeterminate form. of the same kind. Whereas this, after you apply L'Hopital's rule one time, you're to 1 over e to the x, and it's no longer indeterminate, right? Like after we apply L'Hopital's rule here, what happens? One over e to the x, right? And this is what? This is, I mean, you could say that this is type 1 over infinity, right? Type 1 over infinity is not indeterminate. It's just 0. Okay. But people don't usually talk about type 1 over infinity, right? I mean, you could. I did just now. Other questions? Questions are good. If you're unsure about L'Hopital's rule, what you should do is go to the L'Hopital section and just start working problems. Like, just work the odd problems until you understand them. You still have time, right? Now, I don't have a complete solution written to this yet. I got behind this morning. I'll show you what I have. So first of all, this one's integrating factor technique. The integrating factor is e to the x, multiply by e to the x, reverse product rule, integrate both sides, answer. All right. You guys get that one? Yay. Okay, I hope you got that one. This next one, whoa, my bag was falling over. This next one, first of all, you got to use laws of algebra to split off the 2 to the y. Then you separate variables, and then that's a U-substitution. Let u equals x squared. So then you've got 2x dx, so that's 1/2 du. And then I get this, and then I did some algebra. I should probably double check my algebra. I was a little bit in a hurry when I wrote this. But that's what I got. I'm not super confident about what's in a box. I know what I wrote. Pretty sure what I wrote up there underlined is being correct, but solving for y, you might have done it differently, right? Like, for example, you might have left rather than writing 2 to the x squared minus 1, you could write 1/2 2 to the x squared. That would be the same, right? There's a few different other flavor options you got here. Now, technically, I just said find a general solution, right? I didn't say find a general explicit solution. So in my current verbiage, you didn't have to solve for y. I should really give you full credit if you got the thing that's underlined, right? Any questions about that? So you guys understand the drill. Like, if it's separable, you just move all the x stuff to one side, all the y stuff to the other, integrate both sides, you're done. It's not bad, right? Orthogonal trajectories, how do those go? Well, you got to find dy dx, right? And that's a little bit tricky here because of the way where I wrote the c, right? But notice that you can solve for c. C would be 1 minus x squared over y cubed, right? And so when I differentiate that, I get 3. By the way, there's an error in, what was it, quiz? We'll go back to it in a second here. Remind me after this to go back to the error pointed out for you guys. Anyway, so 3y squared c dy dx plus 2x equal to 0, right? So I can solve for dy dx. I get minus 2x. Let me point with my laser. It's more fun. So if I bring the 2x over here, I get minus 2x, right? And then divide by that, gives me this. But then the c I can't leave. I got to change that into x's and y's. I do that with this relation. 1 over c is y cubed over 1 minus x squared. And then multiply stuff out. I get 2xy. Y cubed over y squared is just y. I mean, why not? And then so dy dx, you flip it and you put a minus on it, right? If the line has slope m, the reciprocal, negative reciprocal gives me a line with slope 90 degrees different, right? I mean, a perpendicular line. So the orthogonal trajectories, I just flip and put a minus on whatever I get here. So that's 3 times 1 minus x squared over 2xy, and I have to solve this to find the orthogonal trajectories. And when I did that, I got these things. Yep. Not going to do it. Wouldn't be prudent.
I mean, obviously that makes it a completely different problem. Right?
Yeah, I'm not sure what that means, but I think you're wrong. No offense.
I just thought it was great.
I mean, the problems we had before, this wasn't an issue because we differentiated some equation, C appeared additively, right?
Yeah.
So we just differentiated, the C was gone. So we found a relation between x and y. But the thing is, the C is not an innocent bystander. It's related to how the x and the y are related. And oh man, now you're asking me to explain why.
Well, I just,
Oh,
I thought because it was a C, I had it as a constant, so I figured it was a constant. But
well,
you can differentiate.
I think the problem comes in the, why is it okay to, why flipping dy dx to minus 1 over the whatever's there. It's got to be in that step where assuming c is a constant is a little bit sketchy. But I can't give you a convincing reason. I mean, what you're saying seems reasonable on the surface of things, but I know that this is what we should do. Yeah.
It gave me a different answer. So.
Yes, it gave you a different answer. So I guess the proof's in the pudding. We can pick a point of intersection for the two curves and see who comes out orthogonal to find out who's right. But that seems like that would take 30 minutes, so we'll have to wait till after class. All right, so first one is a trap. It's a trick. It's an easy problem, actually. So cosine of n pi is minus 1 to the n, right? Did you know this? Well, you should learn this. Think about it. Like cosine of 0 is 1. Cosine of pi? Minus 1, right? Cosine of 2 pi? 1. Cosine of 3 pi? Minus 1. Cosine of 4 pi? 1. Cosine of 5 pi? Minus 1. So it goes 1, minus 1, 1, minus 1, 1, minus 1. Stare at it for a second and you'll see that it's minus 1 to the n. So the point then is the cosine of n pi is just plus or minus 1. When you square that, you get 1. So this is just the limit of e to the 1, which is just e. So this one's actually not a L'Hopital problem or anything fancy schmancy. It's just basic understanding of trigonometric and exponential functions as well as limits. That's all. There's nothing snazzy here. This one I haven't worked out yet. And this one is the inverse tangent of this stuff, but the inverse tangent is continuous everywhere. So that means I can pull the limit inside the inverse tangent. And that's a reasonable step because this limit works out to 0. See, because that end of the fourth is the winner. If the denominator has a degree strictly larger than the numerator, that means that after a while that term dominates and it's just like 1 over a really big number. And this goes to 0. Of course, you could prove it by 4 applications of L'Hopital's rule if you'd like. 3 applications of L'Hopital's rule, actually. We'll bring the top to a 6 and the bottom to a 12n, I guess, which goes to 0 clearly. Anyway, this goes to 0, so inverse tangent is 0, 0. How about b? Let's work that out. Now, if that wasn't a 1 over n, right? If that was a n, I mean, this is, what is this? This is 1 to the 0, right? If it was 1 to the infinity, those are both indeterminate, right? Was that right? Anyway, let's work it out. So we have limit n goes to infinity. What is it? 1 plus 1 over n to the 1 over n power, right? So that's exponential of the limit. N goes to infinity. 1 over n, natural log 1 plus 1 over n. So I call this thing star and work on it, you know? So what do we got? Limit as n goes to infinity. And it looks to me like I've got log of 1 plus 1 over n divided by n. I don't know if that's a good move. Well, what is that? That's something, what is that? That's 0. The numerator is what? Natural log of 1 as n goes to infinity? So that's 0. The denominator is infinity. What's 0 over infinity? Take something very, very small. I mean, actually 0 and divide by. Well, take something very, very small and divide by something very, very large. You get something very, I mean, this is not an indeterminate limit. This is just 0. Right? Agree, disagree? So what's that say? So the answer is 1, yeah. Now what you're looking at here might be a typo. I feel like, I think I meant to put n here, not 1 over n. That makes this problem much more exciting, right? If that's n, then instead of having 1 over n here, I have n. And then I have to flip it and apply L'Hopital's rule, and eventually I get to e, which is a problem we worked in class before, right? So this is actually an easier, in some sense. I mean, maybe it's more confusing because it seems like I should do something, right? But, well, sometimes no. A and B, you don't really have to, I mean, and so I think what I'm actually also getting to is, that's not an indeterminate form either, is it? 1 to the, I think we got 1 to the 0 is just, I think 1 to the 0 is not indeterminate anyway, is it? It's just 1, isn't it? Anyway, we have shown that it's 1 for sure anyway, so whatever. Yeah, the indeterminate powers were what? They were 0 to the 0, right? 1 to the infinity, and what was the other one? 0 to the infinity? Oh, infinity to the 0, right? So this one, for example, the exponential, right? You know, if I stick an x here, this gives me e to the x, for example. That's a 1 to the infinity kind of limit. 0 to the 0 would be something like x to the x, you know, as x goes to 0 from the right, right? Or you could do x to the sine of x squared there. Now it's snazzy. Happy. Something like that would be indeterminate. Infinity to the 0 would be something like what? Maybe get something like limit as x goes to infinity of x plus 2 to the, gee, I don't know, 1 over x power. There you go. That would be an indeterminate form. All of these, all three of these you could solve using this technique up here of inserting exponential log and working on the star limit. Do you want me to work one of these out? Yeah? Which one? The top one? So limit as x goes to 0 from the right. What are we looking at here? I said x to the sine of x squared. All right, so that would be exponential of the limit x goes to 0 of the right from the right of the sine of x squared times the log of x. I call this thing star because I have no imagination. Actually, for the same reason I wear the same clothes every day. And recently got this haircut. Let's see here. Oh! Ay caramba. Oh man. Did I say sine of x squared? Why did I do that? I meant, oh, fine. I don't know what to change it to, though. If I bring it downstairs, the sign becomes a 1 over sign, which is known as a cosecant, all right? Now at least I've got, stink, what? Cosecant's 1 over, so that, oh, now it's infinity over infinity, right? Because, again, cosecant's 1 over sine, right? So sine of 0 is 0, 1 over 0, infinity. So this is 1 over x over, what's the derivative of cosecant? Well, it's minus cosecant, cotangent, and then chain rule says multiply by 2x, right? I'm not sure if that's much nicer. Let's see here. Let's simplify it. Limit as x goes to 0 from the right. I mean, I just made this problem up. There's no telling what's going to happen to us if we pursue this. So that's minus the sine of x squared, the tangent of x squared, divided by x squared. And there's a 2. Yeah, thank you. Which is 0 over 0. If you let me cheat for a second here. This is really like minus x squared times x squared over 2x squared. This thing will go to 0 after a bunch of work. And so this is equal to e to the 0, which is 1. I'm cheating a little bit, though, because I'm using things that we don't know yet. So, sorry for that. Yeah, I was using series. It's true. You caught me. The point is that this well, I don't know. I have to keep chasing it. It may be that after we do L'Hopital's rule in the right way, it comes to something nice in a few steps. I don't want to invest more time in it. If we, instead of having sine of x squared, we had x squared, what would have happened? Right, if I, instead of having sine, if I just have x squared, I have x squared, right? I have, then this would go to, the new star would be, limit x goes to 0 from the right of log of x over 1 over x squared, right? And that infinity over infinity, so L'Hopital's 1 over x over minus 2 over x cubed. Sorry, I'm getting squished. So like if I put an x squared there instead of a sine of x, it would have made a reasonable problem, right? The answer would still have worked out to 1 as it happens. But again, that's a quirk of the examples I made up. You could have it work out to something else. All right, so going back to the quiz, let's talk about them. Unless you guys have a question about something in particular. Yeah.
What did you mean by probability distribution again?
A probability distribution means that the integral from minus infinity to infinity is 1. So this here, what happens when you have a case-wise defined function like that? It's even easier than the one we did in class. So like integral from minus infinity to infinity of f of x dx equals what? So if if f of x is 0, for x less than 0, I mean, I can break this into two pieces, right? Minus infinity to 0, f of x dx, right? Like so. But this is 0. It's given to be 0. Integral of 0 is 0. So I really just have to look at the limit as t goes to infinity of the integral from 0 to t. What was my function? ax e to the minus x. It's the integral of x e to the minus x, guys. I think it's minus x e to the minus x minus e to the minus x plus a constant. If I differentiate that, it gives me back an x e to the minus x minus e to the minus x, and then differentiating this gives me a plus e to the minus x. So the e to the minus x terms cancel, and I'm just left with the integrand again. Yeah, that's it. So, of course, I don't think so. Because when I differentiate this, when I differentiate, but when I differentiate, I mean, just check the answer. When I differentiate this, I get e to the minus x, right? From the differentiation of x. When I differentiate that, I get minus e to the minus x, which is plus e to the minus x. So the e to the minus x terms cancel. If you think otherwise, it's because there's another minus you're not accounting for in the UDV BDU chunk.
Yeah.
There are 3 minuses floating about, or a boot. I forget where you're from. Let's see here. Let's bring the a out front. It's a constant, right? So this is minus t e to the minus t minus e to the minus t, and then 0 gives me what? Plus 1. Because when you plug 0 into this thing, the x e to the minus x term goes to 0, and the only thing that survives is e to the minus x. But you're subtracting that because it's the lower bound, which gives you plus 1 rather than a minus 1. I'm almost out of time. That goes to 0, and this is going to go to 0 by L'Hopital's, right? In fact, we talked about that one earlier in quiz 6, right? With n instead of x, but, instead of t. So in total, we get a. Well, that's boring. You make a equal to 1. Aw, man. So boring. So boring. That limit's a doozy. You guys work that out? See if I can find it. Some of these I stole from, when did I steal them from? Was it last semester? I don't know. Something I said? Oh. Let's see here. What test are we on? 2, right? Yeah. I missed problem 3. Oh well. See, problem 3 and 4 last semester, those were supposed to be gifts. Those were supposed to be gifts. But they were gifts that people did not want to take. And so I stopped trying to give them to you guys. Oh, look. Yeah. What in the world did I do? Sorry, I'm intrigued. I'll post this solution for you guys. All right. What is that?
Where'd the L come from?
How did I make this a L'Hopital problem? What did I do? What? Come on. Really? No. I mean, good grief. No. Good gracious. Golly. man, don't tell my students from last semester. All right, see here.
That was actually, oh no, the 0 versus
Yeah, that is an inappropriate use. Okay, here's some better things. So here's the 1 over n to the 4th, sine of n to the 5th. It's just straight squeeze theorem problem. You have sine n to the 5th is bounded between -1 and 1. So of course divide by n to the 4th, and we get this inequality, right? For n greater than or equal to 1. So then by a squeeze theorem, both of these the sandwich sequences go to 0, and so the middle guy also has to go to 0 by squeeze theorem. This one is much like the 3 to the n over n factorial problem on your quiz. You just write out n to the n, which is n times n minus 1, and so forth. And if you look at it, this is greater than what? 1 times 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 n over 1, right? See that? Because what? The denominator is what? It's always either equal to or smaller than the numerator of each of these fractions, right? So we have this, and what does that say? That says n factorial over n to the n over n factorial is larger than n. What happens as n goes to infinity? Infinity, right? This is actually a theorem that I have not emphasized enough in here, but I should. If you can show that a smaller limit goes to infinity, what's to say about something that's larger than the thing that goes to infinity? It must also diverge, yes. So there you go. So there's a proof that goes to infinity. Look at this thing, though. You know, a shocking number of people got this problem wrong. It was disturbing to me. Like, I don't know how to make the least upper bound and greatest lower bound question easier than this. But, whatever. Well, the least upper bound would be 3. The greatest lower bound of this would be 0. So, the point is not to memorize what I just said. The point is to understand the terms least upper bound and greatest lower bound. You know, I mean, you guys. Anyway, so the usual thing, if you have a root plus something, you do a root minus something or something minus the root, and that will make the root go away in the way you want. So basically it's a rationalization trick, and when you do that, it changes from this form to that form. And then if I factor out an x, right? Then, actually I'm factoring out a minus x. So factoring out a minus x, why do I do that? Because if x is going to minus infinity, I can't bring x inside the square root, but I can bring minus x inside the square root. Minus x is positive in this case. That's the thing you can bring inside the square root without changing the sign outside. So that becomes x squared inside, and that gets us to minus 2 over 1 plus 2. And then this thing is not indeterminate anymore. It's just minus 2 over 1 plus 0, which is minus 1. Minus 1? Oh, yeah, okay. I was worried for a second there. So what this shows, guys, is that if you add 1 to both sides, we've got the limit of the square root plus x plus 1 is equal to 0, which shows that this function and that function, if you look at that carefully, you can see that it's a square root minus parentheses x minus x minus 1. So it shows the difference of this function and that function goes to 0 as x goes to infinity. That says that this square root function and that function are asymptotic as x goes to infinity, which is something I haven't talked about in here, right? But it's in the chapter, I think. Or it might not be, but I think I said that part was bonus. I meant it. Since I haven't talked this is the first time I'm mentioning the term asymptotic to you guys. I'm not going to test on asymptotic, okay? But it's important to know about, so I mentioned it. Any question? We have till 4:05, right? Okay. Oh, look, it was still 1 last time. I think I got rid of this one on your test. Your quiz. Problem 12 was I'm going to post this just don't, this isn't quite right. Like my statement of this problem went sideways. You can ignore this. It's not what I wanted. All right, going back to the, where was it? Go back to the quiz. Problem 8. How would you do problem 8? This thing worked out to 0, right? Problem 9? Did it work out to 0? That's what I would have expected. What's that say about, if supposing it did work out to 0, I need to work through it myself again. But if it does work out to 0, and is this an increasing, or I think it's a decreasing sequence, the limit 0, what's that say about the greatest lower bound of the range of the sequence? What is it? It's 0, right? So this one here, I think, look at this, I'm subtracting x to the 1/4 power and 1. I tell you that the root x minus x to the 1/4 minus 1 is greater than 0 for x greater than 7, which is just my way of kindly telling you that this is only, the only improperness is with the infinity, all right? There is actually something unpleasant that happens at 6.7. I threw it into Wolfram Alpha, I checked it out, all right? That's why I put 7 there. So something funny happens at 6.7-ish. But now, what is this saying? So if I'm basically taking the p equals 1/2, right? This much you should definitely know. In order to apply the comparison test, you need what? Something to compare to. What are your main tools? The p integrals, right? We had this result, right? We did this example. Integral dx over x to the p, 1 to infinity, was what? It diverges if p is greater than or equal to 1, or excuse me, other way around, less than or equal to 1, and it converges if p is greater than 1. In fact, we even had the thing it converged to. I don't care about that at the moment. The point is, this looks to me like p equals 1/2, right? And the point is, if this convergence and divergence, if it's the same, here's from 1, you can just as well make this 10 to the 10th. It doesn't change anything, right? Where you start, still the same convergence divergence property, all right? And so 7, 1, anyway, it's looks to me like a p equals 1/2. And so I want to compare it to p equals 1/2, right? I'm hoping it diverges, actually. I'm hoping I can compare it. So if I want to show it diverges by a comparison test, what do I need? I need 1 over the square root of x, right? I need that is less than, what? 1 over square root of x minus x to the 1/4 minus 1. Is that true? It is, right? I made the denominator smaller. I subtracted x to the 1/4 and I subtracted 1, right? So I've made the denominator smaller, I've made the fraction larger. And so I've shown that this is larger than that. This is true for x greater than or equal to 7, right? So that implies that the integral of dx over x to the 1/2 is less than the integral. I mean, you don't usually write that, but I should just conclude, therefore, by the comparison test, this integral diverges, right? Man, this marker cap really is something. As the integral from 7 to infinity of dx over the square root of x is equal to infinity, it implies that the integral of dx over root x minus x to the 1/4 minus 1 from 7 to infinity equals to infinity. And there you have it. I have spent a disproportionate amount of time today on sequences and L'Hopital's rule, right? But as I told you, what? I said probably 60% of the test is on differential equations, right? And then maybe 20% is on, I don't know the exact percentages, but then the other 20% is on chapter 11. And 40% is on chapter 11, something like that. So, alrighty, see you tomorrow.